This etude by Frédéric Chopin is of course anything but random, but it is supposed to depict a device which is random, the Aeolian harp, which is an instrument that is played by the wind. Because it is determined by the wind, the music that comes from an Aeolian harp is unpredictable, and we are reminded of this unpredictability in the opening bars with that insistent repeated note. After all, the wind doesn't remember what it has or hasn't played, so it will tend to be a little bit repetitive, playing what it's already played before. And in this way, the Aeolian harp reminds me of the name distribution we will study in this video, the binomial distribution. Here's the setup for the binomial distribution. We start off with a box of tickets, with some tickets labeled 1 and the rest labeled 0. We'll denote the number of 1 tickets by N1 and the number of 0 tickets by N0, and the total number of tickets in the box by big N. So big N is just N1 plus N0. Next, we randomly draw little n tickets with replacement from this box. So the exact outcome will be random, but it might look like this. There will be little n tickets, some are zeros and others are ones. And because we're drawing with replacement, each time we draw out a ticket, we put it back before drawing again. So it's actually possible for us to keep drawing the same ticket over and over again. And this replacement aspect of the binomial distribution is what reminds me of the Aeolian harp. Now, remember, named distributions like the binomial are used to model random variables. Now, what exactly is the random variable in the situation we've described? Well, if we look at the number of 1 tickets in our sample of little n tickets, that random variable has a binomial distribution. And of course, that distribution is going to depend on how many ones and zeros were in the box to begin with, and the size of our sample, little n. Now, if we know that a random variable has a binomial distribution, then we can just write down its PMF. It's given by the following formula, and notice that this formula is defined for x from 0 to n. And that makes sense because if we draw little n tickets with replacement, we can't get any more than little n ones. If you only draw 5 tickets, you can't get 6 ones. Now, in this video, we'll focus more on how to apply this formula, not on where this formula comes from. Now, I wanted to mention that you'll often see the binomial distribution parameterized a different way, using only 2 parameters instead of 3. And that's because in the binomial distribution, we're drawing with replacement from the box. So each time we reach in to draw another ticket out, the probability of drawing a 1 stays the same. So like with the Bernoulli distribution, it doesn't matter exactly how many ones and zeros we have in the box. All that matters is the relative proportion of ones and zeros. So instead of specifying exactly how many ones and zeros there are in the box, we can specify the fraction of tickets that are ones. And that parameter we typically represent by the letter p. Now the PMF of the binomial distribution in terms of n and p is given by this formula. And you should convince yourself that these two formulas are exactly the same if you simply plug in p equals n1 over n. Let's look at some examples of binomial random variables. First, let's consider the number of tails in 5 tosses of a fair coin. Now, why does this random variable have a binomial distribution? Well, let's set up the box model. To represent tossing a fair coin, let's have a box with 2 tickets in it. One ticket representing heads, and the other ticket representing tails. Now, since we're tossing the coin 5 times, let me represent that by drawing 5 tickets from this box. And I should do that with replacement, because each time I toss the coin, I'm still equally likely to get heads as tails. Now, to be able to apply the binomial distribution, I need to label each of these tickets with either a 0 or a 1. Now, since we're interested in the number of tails ultimately, let me label the tails ticket 1 and the heads ticket 0. Now, when I draw 5 tickets from this box with replacement, the number of ones I get is exactly the number of tails. And we know that the number of ones has a binomial distribution where the number of draws is 5, and there's one ticket labeled 1 and one ticket labeled 0. Let's look at another example. Suppose that we have 4 components, and we know that each component has a 10% chance of failing independently of any other component. And we want to know about the number of components out of the 4 that fail. So why does this random variable have a binomial distribution? Well, let's again draw out the box model. So I'm going to have a box, and each draw from this box is going to represent one component. Now, how many tickets should go in this box? Well, I want to represent this 10% chance of failing. So let me put 10 tickets in this box, and one of those tickets will represent the case where the component fails, and the other 9 will represent the case where the component is okay. And since I'm interested ultimately in the number of components that fail, let me label this fail ticket 1 and the rest 0. So I have one ticket labeled 1 and 9 tickets labeled 0, so that each draw from this box represents this 10% chance of failing. Now, since I have 4 components, I should draw 4 tickets from this box, and I should do this with replacement to represent the fact that each component has a 10% chance of failing independently of any of the other components. Now, the number of 1 tickets in those 4 draws corresponds to the number of components that fail. So I know it has a binomial distribution. But with what parameters? Well, the number of draws is 4, the number of 1 tickets is 1, and the number of 0 tickets is 9.